So the symbol I'm going to talk about is a thing called birefringence, but actually what I'm going to show you first is this beautiful crystal of calcite.
That is a big crystal.
It's an enormous crystal. It's actually just calcium carbonate, so it's the same stuff that limestone and marble are made of, but just in some places in the world it just forms into these perfect crystals of calcite. It's also called Iceland spar, because I think the first found in Iceland. So if you just focus on the square there, Brady.
Yeah.
Okay, now if I put the crystal in there, you can see that the image instantly becomes doubled. It's a strange property of this particular type of crystal that it creates kind of double images of things. But there's another even stranger property, which is that these are now, the individual images are each polarized, and I can show you that by sticking a sheet, this is just a regular sheet of Polaroid, and if I get this just right, so at some angles we see both images, but as I rotate it around, sometimes you'll see one image, and as we keep going around, sometimes you'll see the other image. If I come back the other way again, there we go, they fade between one image and the other, and that's because one of the images, the light is polarized in one direction, and the other image, the light is polarised in the other direction.
Can you hold the crystal? I want to see if I can get your face to double.
I don't know if it... it doesn't work so well.
Hang on.
Okay.
Yeah, it's where... Yeah.
You wanted to try and do the thing with the Polaroid as well?
Go on.
Let's see if we can do that. Okay. I just rotate it around.
Yeah, that works.
Cool.
You can explain it?
Okay.
All right, so
you need to sit down for this. Okay, so it's a thing called birefringence, and it's to do with refraction. Which is the property of material. Every material has a refractive index, and it's to do with the speed of light. Right, the speed of light in a vacuum is always the same, 300,000 kilometers per second, but the speed of light through different materials is different. Basically, the speed of light slows down in different materials, and essentially it's because as the light's travelling through, light's this electromagnetic wave that's wiggling around. The electric fields are wiggling around. That makes the electrons in the material wiggle around as well, and as they wiggle around, they produce electromagnetic waves of their own, which kind of combine with the light that was already passing through. The net effect of all that is to make the light as it travels through slow down. Okay, and we use this all the time. I mean, it's why lenses work, why lenses bend light, and so on. And the reason why, so if we have to go back to our crystal here, right? So if we've got light approaching this crystal, as it approaches, of course, if it's face on, then all the light hits at the same time. But if it's coming in at an angle, then some of the light hits first, and then the rest of the wave hits later on. So as this first bit of light hits, it slows down, but this bit up here that hasn't hit the surface yet is still going at the same speed. The net effect of that is like if you were to drive through a puddle in your car, right? And the puddle only hits one set of wheels. What tends to happen is the wheels on that side slow down, and you'll find your car tends to try and turn that way, right? So it's just the same with light. The light hits here, the bit that hits first slows down, and the net effect of that is that it turns the direction of the light. So one of the effects of light hitting a surface like this, where there's a refractive index in this material, is it changes the direction in which light's going. Okay, that's this effect called refraction. And that's how prisms work and lenses work and all sorts of things like that. So that's a well-known phenomenon. The interesting thing about this particular material is it has different refractive indices, so it slows down the light by different amounts depending on what the polarization of the light is. So one polarization of light gets slowed down more than the other polarization of light. That means that if you've got one wave coming in which is kind of made up initially of both polarizations of light, one of those waves is going to get bent more and one of them is going to get bent a little less. And that means that as the light travels through, the images of something that you're looking at split up because the light gets shifted by different amounts in the two different polarizations.
So how is that possible then? How come that material does this magical thing with light and your window there doesn't?
It's to do with the crystal structure of the glass. So this is a calcium carbonate crystal. Calcium carbonate has this rather particular structure. I'll show you a picture of it here. So this is actually a picture of calcium carbonate. I'm getting scarily close to chemistry here, but basically it's made up of calcium atoms, carbon atoms and oxygen atoms in these various different colours.
Well, that's quite good for you, chemistry-wise.
I thought that's quite impressive. Yeah. Really? It's about the sum total of my knowledge. But if you look at, so this is how they're actually arranged within the structure of the crystal. And what you can see is that there's a kind of a particular axis to this whole thing. There's all these little red groups kind of arranged, sticking out to the sides. And then the calcium atoms are kind of in this more vertical structure. And so you can see there's kind of an axis that runs up and down this particular thing in this direction here. And so you wouldn't be terribly surprised if the properties of this material... So remember what happens is a light wave goes through. So imagine I've got my light wave jiggling, electric field jiggling backwards and forwards as it goes through this way. Okay, as it goes through, it's going to shake these atoms in this direction and shake their electrons in that direction. And it would, because of the structure, the very strange structure of this thing, it wouldn't be too surprising to learn that actually if you try and shake these atoms in that direction, they react differently than if you try and shake them in that direction. And that, at the microscopic level, is the reason why the refractive index of these two polarizations of light, one with the electric field jiggling one way and one with the electric field jiggling the other way, are different. And that's why the light propagates through in a different way. And in fact, since this is 60 symbols, I can even give you a symbol for this. It's called the birefringence, and it's actually called delta N, because N is the symbol that's usually used for refractive index. And what you're measuring here is a difference in refractive index, so it's a delta for a difference, delta N. You're seeing the light, so really you're seeing two images, because the light that came into this thing and kind of was reflected off that blue square, and so the blue light was reflected back to you. One set of that blue light followed one set of paths through that crystal, and the other set of blue light followed another set of paths, and they end up offset from each other, so you see the square in different places. I mean, the light that's filling this room is basically unpolarized, but one of the things you can do is you can always split light up. Okay, this light is kind of randomly polarized, but every little bit of it actually has a polarization. At every point in space, the light is oscillating in one particular direction, and we can always break an oscillation in that direction into a little bit in that direction and a little bit in that direction. So you can always break it down into two individual polarizations. And that means that this complete combination of unpolarized light, all these different random oscillations of the light in all sorts of different directions, we can always break down into two components. And then it's those two components that are acting in these two different ways when you actually end up looking at through the crystal.
Like it's Xness and it's Yness.
It's Xness and it's Yness, exactly. Wow.
The squares move.
Wild.
What's going on there, Mike?
That's just because you're now looking through in different directions relative to the axes of the crystal. And so by looking through in those different directions relative to the axes of the crystal, you're changing the refractive index of the glass.
Where can people get one of them? Everyone's going to want one now.
Go down your gem and geology shop. They're quite often, yeah, they have them. This is the biggest one I've ever seen. I used to have a really little tiny one which didn't look anywhere near as impressive as that.